Hey everybody, I'm Sean Powers, and I am here to help you learn everything, do what you love, and most importantly, be kind. Now, today we are looking at section 1.1.4 of the Linux Plus CompTIA exam objectives. Whether or not you're looking forward to, you're preparing to take that exam, this is great material. That's kind of the case for the entire course. But specifically, what we're going to cover today is everything in these sections right here. That everything else we've covered. So this is the last section. And again, I'm calling this 1.1.4. The objectives only break it up into 1.1, but I broke this up into 4 different sections. So this is 1.1.4. And we're going to cover things like different types of storage. We're going to touch on what RAID is and how it works. Not the command line stuff, just conceptually what it does. Because again, this is storage concepts. We're going to touch on RAID later in the series, but this is just so we get an understanding of what it is. So yeah, we're going to cover that. We're going to just talk about storage stuff here. Also, we're going to learn how to compile a package from source. Honestly, it has nothing to do with the storage concepts. It's just that's the last little bit. So I'm just kind of tacking it on the end of this video rather than making like a 2-minute video to stand alone for just that. So it's like bonus content for this thing about storage. Anyway, I did blow this up because if you look partition, it's supposed to be partition type or partition types, but they actually made a typo, partition typo, which I just thought was a hilarious sort of Inception based typo, right? A typo of typo. Anyway, nonetheless, that amused me, so I wanted to point that out. But right out of the gate, I want to cover the most text heavy slide because hopefully your attention is still, you're not bored yet, right? I'll fix that. We'll bore you. No, but there are 3 types of storage concepts that are specifically mentioned in the objectives. And these are, I mean, it's a good explanation of the 3 different kinds of ways to think about storing data. Now, the first one is file storage, and that's what we think of generally when we think about storing files is, you know, you have file names and directories, and this is just where we store our files with a file name .extension or whatever. General file storage on a hard drive that has a file system like ext4, btrfs, or ntfs if you're in Windows, that sort of a thing. This is the traditional way that we think about storing files, but there's other ways too. For example, block storage. Now, block storage is a way that we store data in big chunks. It doesn't have metadata. It doesn't have file names. It's just big blocks of storage where we write whatever we want to it, right? The blocks don't know what they contain. They just know that they're a block of data stored somewhere. The thing that is great about block storage is that it's extremely fast. So we'll do things like use block storage for databases a lot. If they have to write constantly, they need really good performance. Block storage is where that happens. Again, there's no metadata. The block storage is just a block of data. You have to know what's there kind of at a different layer, right? When you're writing to block storage, you need to keep track of what data you're putting where, because the block, you don't know. All right. File systems are often built on top of block storage. Hopefully that makes sense. You might remember from a previous video, we talked about block devices like hard drives, and that's kind of the same concept, but file systems are often built on top of block storage so that we know what data is in those blocks. And some things you've probably heard of, like iSCSI. iSCSI is block storage, and we usually use iSCSI to connect remotely to a storage system like a SAN, again, right here, a storage area network. And on top of that iSCSI chunk of blocks, we will often put a file system so that we can do file storage. But block storage is its own beast, right? It's how we store data. And then the new kid on the block that is all cloudy, if you will, is object storage. And this doesn't just have to happen in the cloud, but that's where it's most commonly used. And it's very unique and very different from the other types in that the entire object that you're storing, whatever that object can be anything, but it's just a thing. Like it can be a file, it can be whatever that object is. We reference it as an object, and each object has a UUID, a unique universal identifier, and that is how we reference it. It doesn't have a file name. I mean, I guess you could name the file whatever the UUID is in the end, but you access it via API, right? This is how programmers can store data without writing to a file system. It's object storage where they can store it like in a database with blob storage. So if you've heard of blob storage, I think I got ahead of myself down there. Blob storage is object storage. Amazon S3, where you store things and reference them using a programming API. That's the big difference with object storage, is that you can only access it via API. Now, there can be a third-party tool like Add Another Layer where you sort of map the API onto some local file system so you can see the contents of like a bucket or something. But the actual files, not files, that's a poor choice of word. The actual object is accessed via API. Now, it is slower. It does contain a bunch of metadata, so you can put a description of what that chunk of data is that's stored as an object. But it's generally slower than like block storage, and it's also a lot cheaper. But the big thing is it's programmatically accessed and it's very easy to scale, right? I mean, everybody's familiar with Amazon S3 these days, and you basically just store and pay for as much data as you need via the API using S3. And that's where object storage is. And again, you can store objects like in a MySQL database. It's not a terribly great way to go. I mean, it's good for some things. The bigger a thing gets, I don't know that MySQL is ideal, but sometimes you can store thumbnail pics as blobs inside of a database. So it's possible to do something other than just Amazon S3, but that's the most common thing. When we think about object storage, at least for me, I think of, programmatic stuff that references S3, and that's the different types of storage concepts. Now, this objective did specifically mention the different types of partitions. Actually, it referenced typo partitions or partition typo, but the types of partitions, we already covered this, so I'm just going to gloss over it, mentioning one more specific thing. We basically have two different types of partitioning schemes, right? If your system is running BIOS, it uses MBR, master boot record, and that's where the information about what's on the hard drive is stored at the very beginning of the hard drive, and then you can chop it up into partitions using the master boot record. It's kind of like a table of contents that points to where the partitions are on the hard drive. If you have a UEFI system, it uses the GPT, this is kind of cool. It's like I've said Inception already in this video, but GUID, the globally unique identifier, that's what this acronym is. But GPT, is the corollary to MBR. GPT, the G actually references a different acronym. So it's like an acronym wrapped inside of an acronym. So this is a GUID partition table, or globally unique identifier partition table, if you want to spell it all out. And this is just a newer version of MBR. Now, the thing I wanted to mention, we talked about this before, where, it has its little partition table, but it also scatters the information in multiple places in the drive in case one gets corrupted and there's CRC error checking. You can have more than 4 partitions. But the thing I wanted to point out, notice I painted this blue. The cool thing that GPT does is when you partition a drive using GPT, it creates kind of like an emergency or a fake master boot record. And the reason it does that, it's a fake master boot record, and all it does is it says, I'm a master boot record and I have one partition that fills the entire drive. And the reason that's important, if you put a hard drive that is partitioned this way into a computer that is running BIOS and MBR, and it didn't have this like safety feature, the BIOS computer would say, oh, look, it's a blank hard drive. There's no master boot record. And you might accidentally just format it and wipe everything out. What this does is it gives you like a safety net, where if you put a GPT partitioned drive into a system running BIOS that expects MBR, it's going to see this tiny little MBR or fake MBR that says, I'm not empty, I'm full. And that's enough to give you a hint like, oh, there's already something on there. So that's really kind of a neat feature that was backwards, looking back at it's not exactly backwards compatible, but it's backwards honoring, I guess, if I had to pick a way to say it. And that's just a really cool thing about GPT, and good to know that if you put a drive in and it says there's one full partition, it probably means it's a GPT drive. Okay, so now you know. Now, the next thing we need to cover is fuse, or...
And now another controvertible episode of
File Systems in User Space,
starring the voracious Captain Link Hogthrob, the gluttonous First Mate Piggy, and the esurient Dr. Julius Strangeport.
Yeah, okay. File system in user space is what fuse stands for. It's kind of a weird acronym. It's like the F in file system and then use in user space. But what this means is you can mount something on your local system as a user. You don't have to be root to do this, because normally, because mounting a file system requires kernel access and root level kernel access, normally you can't do that. But what Fuse does is it allows you as a user without elevated privilege to mount a file system on something that you have local permission to do, like in your home directory, and it allows you to mount and unmount something without needing root access. It's just a really great way. And there's lots of things that take advantage of this. I mean, I think USB drives too, you can actually mount like a tar.gz file and have it appear as the file system, and you're just kind of looking inside the compressed file as the file system. There's a lot of cool things you can do. One of my favorite is SSHFS, which I'll demonstrate right now. So here I'm just on my Ubuntu Mate system. I installed the package SSHFS. It's just a package you can install. And let's do ls. Okay, I'm going to, first of all, SSH to a server on my network called Whisker. All right, so we'll go into Whisker. I'll put in my password. If I typed it right. Yes. And if we do an ls, we're going to see we have two files, remote server file.txt and symbolic link to dhcp.conf. Okay, so this is a symbolic link. This will be actually cool to point out later too. So dhcp.conf points to etc. DNS mask in my dhcp.conf file. Okay, so that's on my remote server called Whisker. So let me exit. I'm back on my Ubuntu Mate box. I want to create a folder. So mkdir Whisker. And now we just see it's a folder. If we look inside Whisker, there's nothing there. I just created an empty folder. But if we were to do SSHFS and mount the remote, or specify the remote server, so in this case, Whisker :home s powers, and I want to, and then tell it where I want to mount it on the Whisker folder that I just made, press enter. It's going to ask me for my password. And I typed the password wrong. Okay, I typed the password right that time. And now, if we look in Whisker, we're going to see those same files, because right now, using SSH, we've actually mounted a Fuse file system, or a file system in user space, right here on the thing. If we do df-h, we're going to see Whisker home s powers is right here mounted on that local folder. And that allows us to use it as part of our local file system, but it's mounted over SSH. And you'll notice I didn't type sudo for any of those things. So if we do ls-l Whisker, this is the cool thing I wanted to show you. A symbolic link points to etc. DNS mask dhcp.conf, but it's pointing to that folder. It doesn't exist on Ubuntu Mate, so that's why it's red. It's a broken link on this computer, but it still is mounted on my local file server, or on my local file system in Ubuntu Mate. And again, I didn't have to become root. That's really the big thing, is that it's user space file system mounting, because I can type umount for unmount Whisker, and it unmounts it. And now if we look inside, there's nothing there, because I've unmounted that remote SSH file system. So Fuse is actually really cool, and it allows you to do a lot of things that you normally would have to have root access to do. I know this seems like just a pew-pew shotgun effect of way of teaching things, but there's just a bunch of concepts that are loosely related. One of them being RAID, or a redundant array of independent or inexpensive, depending on who you heard the acronym from, disks. So a redundant array of independent disks is how I've heard it most commonly used. And this allows you to take a group of hard drives or disks or block devices and use them in a way that have pros and cons for different levels. We're going to look at 3 different RAID levels, which are 3 different ways that we can use drives for either speed or redundancy, or just to get the most space out of a bunch of drives, because RAID also allows you to use multiple disks as one volume, so to speak. And that's kind of a really cool thing to do, but that requires like parity, and we'll show you in the picture. But here's the thing too, I'm going to use, I'll show you just here. Let's go to the slide. So if you trained with me before, you probably recognize this guy. He is my RAID dragon, and I used it over 10 years ago, and it was such a poor drawing and it made me laugh. I decided to use it every time I explain RAID. So this is one of those times. And I want to talk about conceptually what RAID does. Now, what RAID is you take a bunch of drives, like in this case, every one of these purple boxes is representing a hard drive, and they're each 10 gigabytes in size. And that'll be important when we talk about how much usable space and stuff. The metaphor that I'm using here is, this is the crown, And this is our data loss dragon, or our data corruption dragon. And every purple box is a knight who is trying to protect the king or queen from data corruption. Anyway, basically the dragon can't get to the crown, or the data is corrupted. That's the metaphor. It's a loose metaphor, but you know, the dragon's cute. Anyway, RAID 0 is our first level of RAID, and this is the first arrangement of drives that we can use. And basically, when you have RAID 0, it's called a stripe. And the reason it's called that is because all of these drives are added together, and that gives you the total usable space. So we have 4 10 gigabyte drives, and that means that we have 40 gigabytes of usable space. And it gets even cooler. When you write a file, let's say we have a file here, and let's say it's a 4 megabyte file, because that makes for easy math on my part. When you write the file to the RAID array, which is this group of 4 disks, it actually writes a quarter of the file to every drive. So that means it's going to write, like if you save this file, it's going to, at the exact same time, save 1 megabyte or 1/4 of the file to the drives. That means you can save a 4 megabyte file in the amount of time that you would normally save a 1 megabyte file, because each drive is saving at the exact same time. So reading and writing from a striped array is very fast. It's very, very fast. That's actually why people use RAID 0, is because, well, one, you get full use of all of the hard drive storage space, but also it's extremely fast because of the way that it writes data in stripes on each hard drive in the array. But there is a downside, and you've probably already figured it out. Like, yes, if we do this, we have 40 gigabytes of usable space, and it's extremely fast. However, what happens if one of the drives fails? Let's say that our dragon here takes this drive out. It flames this knight, and this knight is now dead. Well, now our entire array, all of the data that we have stored, is useless. In the dragon metaphor, it's because now the dragon can go right through and get to the king. But in our data world, in our data metaphor, if you will, what good is 3/4 of anything? You know, I mean, if you have a file and then all of a sudden you have 3/4 of the file, that's no good. It's useless. And because of the way it's striped across all these drives, if you lose one drive, no matter how many drives are in your striped array, if you lose a single drive, all of your data is corrupted and no good. So it's fast and it's high capacity, but it's really dangerous, and you don't want to store data on there that you couldn't lose. So that's what RAID 0 is. Now, RAID 1 is almost the opposite approach, because with RAID 1, which is called a mirrored array, you have the same thing, the 4 10 gigabyte drives. However, you only have 10 gigabytes of usable space, because every single drive is a mirror of the other drives. That means no matter how many drives you have in a mirror, they all have a copy of the same data. Now, you get no speed increase from this, because every time you write that file, it is writing the entire file to all 4 disks in our array. So you get no speed increase. It takes the same amount of time as it would to save to a single hard drive, because you are saving to 4 hard drives at the same time. So no speed increase, no file size increase, because up here we had 40 gigabytes of usable space. Here, since there's a copy on every single drive, we only have that 10 gigabytes of usable space. So there's no speed increase, there's no storage size increase. Well, what on earth would we want to do this for? Well, of course, again, you've already figured it out. Redundancy. Our data is stored on every one of these drives. So if the dragon were to take out this one, we still have 3 copies. We're still fine. And then the dragon keeps going and takes out this one, still fine. Takes out this one, still fine. 3/4 of our drives are gone, and we still have a complete set of our data, and we're all good. So that's what a mirror does. It sacrifices the potential speed and the storage of all of the drives and gives you redundancy, so you don't have to worry about a bad drive ruining and deleting all of your data. Now, RAID 5 is a little bit different. It kind of tries to split the difference, and it uses technology that I won't be able to explain super fast. But how RAID 5 works is we have these same 4 drives, But instead of adding all of the space together or just taking the one, how RAID works is the total number of drives in your array minus one drive's worth is how much storage you have. How that works is when data is written to a RAID 5 array, it is written across multiple drives, kind of like a stripe. However, each drive also has a little section on it called the parity section, or where it stores parity information. And how that works, again, is beyond the scope of this video, but what it means is, in practice, you have, so n, that's a terrible n minus 1 is how much storage you have. So we have 4 drives here, so we have 4 10 gigabyte drives, so n minus 1 means that we have 30 gigabytes of storage. Okay, so that's how much storage we have, which is quite a bit. It's obviously more than RAID 1, not quite as much as RAID 0, but here's where the magic happens. Since the drives store data across multiple disks, along with a small portion of each disk for parity, that parity allows us to rebuild any single drive if it fails. So that means if the Dragon were to take out this drive, these 3 drives, along with the parity on those 3 drives, will allow us to still have a full copy of all 30 gigabytes of data. And it doesn't just have to be this single drive. It could be any drive. Well, it can only be a single drive, but it doesn't have to be a specific drive that can fail. Any of these drives, as long as it's just one, can fail, and the remaining 3 still have a full copy of all the data on the array. It's really, really amazing, and RAID 5 is a great way to take advantage of the bulk of your storage while still giving you the ability to lose one drive and not lose any of your data. So that's storage concepts. Again, the bonus content, I just want to finish off this objective, is how to compile from source a package and install it on your computer. It's a little bit weird of a throw out thing they put in here. But basically, if you have ever heard of like compiling a program, make, install, that sort of a thing, that's what we're going to do. And it's basically taking the source code, compiling it on your computer, and installing the binary that comes from there so you can use it on your computer. It's not usually how we install packages on a Linux box. Usually we use the package manager that comes with the distribution, but sometimes, like if you've written the code or it's a package that's not in the package manager, you may have to compile something, and that's what we'll do really quick. And there's a cool package out there. It's called Hello, for like Hello World, where it allows us to do the whole process, but it's a pretty simple throwaway program. Now, Linux distributions almost never come with the compiling tools, the build tools installed by default, and it's different to install them on a Red Hat-based system versus an Ubuntu-based system. So I'm going to show you really quick how you would install the programs that would allow you to compile a package. And so here we are on Rocky Linux, which is like Red Hat Enterprise Linux, and we would just do sudo DNF, or you could do yum depending on what version you're on, and it's group install. We'll look at package management in a later video, but group install, and I gotta look, it's called development tools, and we install this, ask for the password because I did sudo, and then it will install a package. It's a group where it installs all the things you might need for making and compiling a local program. So we would say yes, and we would install that, and then we could go through the process of downloading and compiling a package. I'm going to do the same thing over here in Ubuntu. In Ubuntu, it's a little bit different. You actually just do sudo apt install build dash essential. Again, different process, but same type of thing, slightly different packages. But this is going to give us the ability to install stuff. And it looks like I already did it. All right, I already did that earlier, but that's how we do it on Ubuntu, is install build dash essential. Okay, and then like I said, it's not very common to do it anymore, but the GNU.org website has a really cool package. It's just called Hello. So I just went to ftp.gnu.org/GNU/hello, and this is the package. I'm just going to download it by clicking Hello. It looks like version 2.12.tar.gz. This is the source code, so I'm going to click on that. It's going to download it. It completed because it's super tiny. go back to the command line here. Let's go into my downloads folder. We should have, sure enough, hello. And I'm going to extract this. So tar zxvf hello. It will extract it. And now we have a folder called hello. So we'll go into there. And now this is what a source code package looks like. Like if you download a GitHub repository, this is what it's going to look like a lot of the time. If it's designed to be compiled, this is what it's going to look like. And basically we start with running, so ./configure, which is going to be a script in this folder. You can see it, it's right here, an executable script. And this will do a couple things depending on the package. It will make sure that you have all of the libraries it's going to need to compile itself. And it will tell you if it doesn't, and it'll error out and say, I need like Python this before I will compile. And then you'll download that, install it, and then run configure again. It checks to make sure everything it needs is there. And then it will create the files that will be used at the next step. Okay, so always run configure until it completes without any errors. So in this case, we'll do .configure, press enter. It's checking for all of the things to make sure that we have everything that we need. Okay, no errors. So it created, see at the end here, once it checks that it has everything, it creates all the files it needs for compilation. And then we just type make, and then it will actually compile the code using the appropriate compiler. And again, this is a small program, so it's done before I finish the sentence. And now if we look, there's probably going to be an executable in here that wasn't before. Basically, hello is the executable, but there's one more step we can do. Most makefiles, not all, most makefiles come with an install option as part of make. And so we have to type sudo, because what install does is it takes the binary that was just compiled and puts it somewhere on the system, like in your bin folder, your user local bin folder, so that you can execute it without using the entire path, right? It just installs it so it can be used on your system. And sometimes it will install other parts that it needs. Like let's say it compiled its own libraries, it will copy those libraries to the appropriate folder on your system. So we're going to do sudo make install. And it did it. It copied all of the stuff to where it needed to go. It looks like it installed a man page for hello. It installed, so user local there, and it installed it in user local bin, which is the place that you would normally install something for a local package. We covered that in the, directory video a couple videos ago, but it installed it in user local bin. So we could type which hello, and it will tell us where it lives, user local bin hello. So now it's an executable on our system. Hello, and it will say hello world. I mean, that's all this package did, but that takes you through the entire process of downloading, compiling, and installing a package from source on a Linux system. And that's the end of this video. I hope you're enjoying this course. We finished up 1.1, so that objective is completely done. And I'm gonna close with a line stolen from Hank and John Green. Don't forget to be awesome. See you next time.